Let's see, so as we work with geometric sequences, we previously completed the arithmetic sequences, and arithmetic sequences were when we had a common difference. Something was being added or subtracted to create each additional term, and that was a common difference because it was the same change each interval. Well, what we're going to talk about now is geometric sequences, and the geometric sequences are going to be multiplication and division. So if something appears to look like multiplication or division, that's geometric. And really it's all multiplication, but sometimes when we divide by a number, it looks like division versus multiplying by a fraction. So all of those things, work together here to form this geometric sequence. We have talked about the explicit formulas, and what we have here is, if you look, this thing right here, that thing right there is going to be the explicit form of a geometric sequence. We've already covered the AN. The AN is some future number. We don't know what it is yet. A1 is going to be your first term in a sequence. Just taking a quick snapshot down here at number C, or letter C, the first term is going to be 2 to the third power. R is going to be my common ratio, and the common ratio is what is being multiplied or divided for each consecutive term, and then there's no change in N for its value. So as we come over here and we look at identifying a geometric sequence, we want to find out if it has a common ratio, and we have looked in the past and seen how to find a common difference, but to find a common ratio, we're going to take one term, some term, and divide it by the term before it. So in this case, if we look at your example here, what is the sequence? Is the sequence geometric? Well, if it has a common ratio, that means it's geometric. So if I take one term, if I take a 4 and divide it by 2, I get a 2. If I take 8 and divide it by 4, because 8 and 4 is its previous term, then I get a 2. So it appears to be a common ratio of 2. So is this sequence geometric? Yes, because it has a common ratio of 2. Looking at number 3, if I divide 5 by 1, I get 5. If I divide 9 by 5, I get 9 over 5. Well, that tells me right there, these two things are not the same. Therefore, we do not have a common ratio. So it is not geometric. Looking at letter C, we can go ahead and take a to the 7th divided by a to the 3rd, and it turns out when we do our exponent rules, we find out that is 2 to the 4th. Then if we take the next term, term 3, and divide it by term 2, then we get again x to the 4th. So those two are the same, so we do have a common ratio, and that common ratio is going to be 2 to the 4th. And let's see here, so now that we have identified geometric sequences, let's try to analyze these geometric sequences. So what is the second term of the geometric sequence 3 and a blank and 12? Well, I'm trying to find the geometric term, and what I can do, there's multiple ways to do this actually, but what they're trying to get us to do is use some of our information. So we have our formula, the explicit formula, and we know that we need to find some term, we need to identify our first term, we need to identify our ratio. And in this case, we are given the second term of a geometric sequence. What is the second term? Well, we know the third term, we know the first term, so we can use that to identify what our common ratio is. And once we do that, then we can go on and do more. And I can turn around and say, okay, well, 12. 12 is A3, so I can replace AN with A3. A3 equals A1 times R to the 3 minus 1. Well, we don't know what R is yet. but we do know what A is. A1 is going to be 3. So we can go ahead and simplify here. I know A3 is 12, so I've done some substitution here. A3 is going to be 12, and it is going to be equal to A1 is 3, 3r squared. I'm going to divide both sides by 3. And then that way I get 4 equals r squared, or when we find the square root of r squared equals the square root of 4 squared, so then r equals 2. So if my common ratio is 2, well, plug that back into my equation right over here, and it's going to turn out that that number is going to be 6. There you go. There you have it, analyzing a geometric sequence. And here, if we wanted to find out what is the third and fourth terms of a geometric sequence, well, we can do the same thing. We are going to use this a to the fourth, and I know that when I look for when I'm using my explicit formula, I need to find an. Well, an is going to be a to the fourth. Okay, we're going to use that value. We know what a1 is. That is going to be 2. We don't know what our ratio is yet, but we do know still the n. The n is valued at 4 minus 1 versus n minus 1. So now we simplify. I've replaced here. Well, we know that a4 counts for 128, so we've done a substitution here. Substitution, that was some of the given information. We can divide both sides by 2 to get rid of this coefficient right here. So we can divide that, and then we end up getting 64 equals r squared. 64 equals r cubed. Now once I have r cubed, I can go ahead and find the cube root of both sides. Cube root of 64 is going to be 4. Cube root of r cubed is going to be r. So I know my common ratio is 4. Coming back over to my problem, I can substitute that information in to get my next two terms. Point are, identifying a geometric sequence appearing to be multiplication or division, analyzing a geometric sequence, looking at it, being able to discover what is my r, what is my a1, what is my r value, what is my n if I need to calculate a future n term, which is what we did here. We used a n basis of a4 here to calculate some stuff. Okay, continuing with the geometric sequences, and one of the reasons that we learn math is learn how to apply them in realistic scenarios. We're going to use the geometric sequence to try to take a real life situation and turn it into a geometric sequence. So this example, when a ball bounces, the height of consecutive bounces form a geometric sequence. So that means it's either appears to be multiplied or divided consistently. And what are the heights of the fourth and fifth bounce? Well, we know the height of the first bounce, right? Here's A1. The height of our first bounce is going to be 100. I'm assuming 100 feet. The height of the second bounce is currently unknown, but we do know the height of the third bounce, and that is going to be 49. So if I come up here and I look at this situation, I know that I have here A1 is going to be 100, don't know A2, A3 is 49, and don't know the fourth and fifth issues yet. What we can use, though, is we could try to figure out, given the information that we have, using our explicit formula. This is our geometric explicit formula. AN equals A1 times R raised to the n minus 1 power. Now, R is going to be the common ratio that we learn, and we learn the common ratio by taking one value and dividing it by the previous value. So we know that we have A3. Here's A3, so we can substitute that in for n. So we have A3 equals the first number, A1, right? A1 is going to be 100 times R raised to the n minus 1, or since n is now 3, it's 3 minus 1. Given that, we do some substitution, and we know that R3 was 49, so we substituted in 49 equals 100 times R squared. 3 minus 1 is 2. And we can divide by the coefficients on both sides, which is 100, and we get R squared. R squared is equal to 49 over 100, which, doing the square root, is going to be R equals 7/10. So if I know my R now, R is now 7/10, I just need to be able to substitute that back in right here, substitute it back into my original formula, or better said, right there. So substituting that back in, it looks like I have A4 is going to be 100 times 7/10 to the third power, which is going to give me 34.3, and then A5, doing the same substitutions, will give me 24. So we were able to find here that the heights of our other terms, or our fourth and fifth term, those unknowns, were going to be 34.3 feet, I guess, and 24 feet. Going to our next example, it asks us to find the height of the 10th bounce. What would you use, the recursive or the explicit formula? Oops, got a little typo there. Or the explicit formula. Well, we haven't really talked about the recursive formula, but we would use the explicit formula to find an exact location, and by doing that, we can find it simply by estimating somewhere around 4 feet, and then the sixth one would have been 16.8. So let's see here. Moving on to the geometric mean. When we did the arithmetic mean, that was the average. But since we were talking about multiplication and division here, when we talk about geometric means, we have a different mean formula, and that is where we take one term, in this case the 9th term, times the 11th term, and we find the square root of that, which is then going to give us the term in the middle, the 10th term. Okay, so we have 3 consecutive terms. Their geometric sequence, it allows us to find the middle term. So in doing so, let's get rid of that, and let's look at our question. And our question is something along the lines of, the 9th and 11th terms of a geometric sequence are 45 and 80. What are the possible values of the 10th term? Okay, so 10th term, so we take the square root of A9 times A11, so the 9th term times the 11th term, which was 45 and 80. So 45 times 80 came to 3,600. So again, the square root of 45 times 80 equals the square root of 3,600. The square root of 3,600 is 60. So my 10th term is going to be 60. And there we go. We don't know right here what the 8th term is, but we could figure it out later on. But we do have 45, 60, 80. So we are changing in some geometric value. And then it says this next example. Well, let me go back here. Look at this. To find the geometric mean, multiply 2 terms and then find the square root of that, which is exactly what we're doing. And moving back over here, what are the possible values of the missing term in this geometric sequence? Well, we had 28, some blank, and then 7. And I don't know what term numbers these are, but there are 3 consecutive terms. So I should be able to say that one term times the other term is going to be the square root of one term times the other term is going to be the square root of now 196, because it was 28 times 7, and the square root of 196 is going to give me 14. So I should be able to say, okay, that missing term is going to be 14, and that is my geometric mean. Some of the things that we have covered up until here. Going to what we just covered here, we did use the real world scenario using geometric sequences, then the geometric mean or the geometric average between three consecutive terms. And that is that for geometric sequences.